Hi, and welcome back. Today we're going to see some new exercises, and they're going to be about subspaces, which is a topic we've already take care of last time, and also orthogonal subspaces. So I'm going to start showing the solutions of these three exercises, and when necessary, I'm going to introduce some bits of theory. Okay, so here we have four vectors, and in principle, this one depends on a parameter, a real parameter, and I'm asking at least the first three questions ask things about linear independence and generation. So let's look at it and let's see. So the first one, for which t, this one is linearly independent and it generates. I mean, generates can't be, because it's just one vector. And 1 is less than 3. What about independence? Well, let's try. This means lambda times t equal to 0, and if t is different from 0, then you can conclude that lambda is necessarily 0. So in that case, it's independent. In that case, okay. But if t is equal to 0, then it's the zero vector. The zero vector. So the zero vector is not independent. This is what we know. Okay, so then let's see the second. So we're taking these three vectors and we're asking whether they are linearly independent and or they generate. And you know that a way of doing this is to consider the matrix which has the columns given by these three vectors. And then, since there are three vectors in R3, they're going to be independent if and only if they generate. So, and independent means that the kernel of this matrix has to be just 0. So let's just find the kernel of this matrix. So we're just going to solve this linear system. It's very kind of straightforward. So let's write this matrix, which is t, t, t. The second one is 1, 2, 1. And this one is 0, 0, 2. Okay. And this is... Okay. We can try and do the Gauss algorithm. So this is just the zero vector, so I'm just writing this matrix here. So I'm, for example, subtracting the first row and 0, 0 here. This is going to be again this 2 minus t 0. This is sorry, just subtract. This is 1. Okay, and this is again, this is 0, 2. Well, it was kind of quick, so we conclude conclude that you get this linear system here, tx plus y is equal to 0, then you have y is equal to 0, and then 2 times z is equal to 0. Is that correct? I hope so. I think so. It's just subtracting. Yes, looks fine. So we deduce that y and z there have to be equal to 0, and then you have that tx is equal to 0. So there you have, if t is different from 0, then x is again equal to 0, and if t is equal to 0, then actually you don't have any condition here. So so any x will do. Let's say that, in the sense that if t is equal to 0, then any x will be, any x together with y and z equal to 0 will be in the kernel. So if you want, in this case, things, if t or again, you can find the basis of the kernel if you want. It's very easy, but it's like this, if t is equal to 0. But in any case, so you conclude that if t is different from 0, then this is a basis because it's independent, hence it generates. If t is equal to 0, it is not independent and also not generating. Okay, fine. So so the third one asks for which t is linearly independent and for which t it generates, the set of all these 4 vectors. And here there is something from the theory that since you have 4 vectors in R3, never independent, but in principle they can generate. So let's see, perhaps, if we are lucky, and let's see if the last 3 vectors do generate, perhaps. That's just a hypothesis we make here. So you consider the matrix with the last 3 vectors, and you try to reduce it as usual. So subtract by 2 times the, so this is 101, this is 0, 0, minus 2, and again here subtract. Did I subtract well here? Yes, I did. Yeah. Okay, this is again 0, 2 minus 1. Okay, fine. You can exchange, if you want, the second and the third. 0, 2 minus 1, 0, 0 minus 2. Well, it looks like that we got a matrix. It's easy now if you look at the system associated to this. I don't know. And so from here you get z equal to 0, and then you get x equal to y equal to 0. So it's clear now that these 3 vectors are independent, so they generate. These 3 vectors generate. So generate, and in particular if you add a vector to any set of generators, then you get again a set of generators. Okay, very good. Now, I mean, this was just a recapitulation on subspaces, and now there is something new, namely we are asked to find a basis of the orthogonal of this orthogonal space. So first, just review here in this case, just in this case. So if you have a subspace V in, let's say, Rn, if you want to take n equal to 3, it's fine. Then you can consider its orthogonal, which is defined as the vectors W in R3, Rn, such that if you take the scalar product with V is equal to 0 for all V in V. And I mean, the scalar product here, if W is this vector and V is this vector, then the scalar product is just the sum of the components, the product of the components here. Okay, and just a remark, if V is the span of few vectors here, then it's easy to check that the orthogonal of V can be obtained as such that you can just check orthogonality against the generators of the span. So here, okay, very good. So there are vectors who have to be orthogonal to all vectors in V, but if V is generated, is the span of some vectors, you can check that it's the same. You can check just orthogonality with the generators. Okay, fine, this will help. So, I get to already add. Good. So, we want span of V true and take the orthogonal of this. So, V true is 1 true 1. Okay. Is this correct? I hope. Yes, V true. Yes. So, from what we said before, this is just we can describe it as just the vectors. I don't know, x, y, z in R3, such that, well, they are orthogonal. Did I write it? Yes, okay. So, this is actually just this thing, so just compute x plus 2y plus this is equal to 0, and we are asked to find a basis. Yes, a basis. So we have one equation here. So this is a relation between these variables. So you can say, for example, take I don't know x equal to t, y equal to s, some parameters if you want, and then the other is going to be minus x minus true y, so it's going to be minus t minus true s. So you can write, if you want, as like t s and the other minus t minus true s. And if you like isolate things, so you have t 0 t plus minus t, plus 0 s minus true s. Yes, and you can isolate the parameters like this. So 1 0 minus 1, plus s, 0, 1, minus true. So you find out easily which is now you have that is a basis of this orthogonal space. Very good. And you can check indeed that if you want to double check, then just do, for example, the scalar product, the inner product with this. What is this? Is 1 to 1, and check that it's correct. So this is indeed 1 plus 0 minus 1 is 0, and the other is 0 plus 2 minus 2 is 0. Okay, it works. So we are good. It works. Okay, fine. Now the last one. We want an orthonormal basis of this other subspace V2, of the span of V2 V3. So take span, which is span, I think 1 2 1 0 0 2. Let's double check, of course. It's very important not to make stupid mistakes by copying things. So 1 2 1 0 0 2, it's okay. Okay, very good. And we want an orthonormal basis. And well, here you have the famous Gram-Schmidt algorithm. And yeah, it's best explained when you see it in action. So the idea is that you start with a vector, you normalize it, and then you do some orthogonal projections, and after this you end up with something which is an orthonormal basis. I want orthonormal basis. And yeah, orthonormal basis means a set of vectors which is a basis, and it's orthonormal in the sense that, let's call this this with these two vectors. So in this case we want that they are orthogonal, and also their norm, which is this has to be 0, and also this, sorry, not 0, what, 1, of course, 1. You should always remember that you have a famous orthonormal basis of Rn, which is given by the vectors like this, the canonical basis vectors, you know, and it's an orthonormal basis. But in general there are many orthonormal bases, and you can construct them starting from any basis. You can like modify it and build an orthonormal basis, and the way is by this Gram-Schmidt algorithm. And I mean, it's easier if one sees it in action, and then like just writing it with the formulas. So the idea is that you start with a vector, you want to normalize it and project, and okay. But I mean, here we could start, for example, with this vector, normalize it, and then do stuff. Or start with this vector, normalize it, and do stuff. I mean, and actually it's easier if you start with this one, because it's like just a multiple of one of the canonical basis vectors. So it's very easy to normalize it. So take with the algorithm, you would take, let's say, W3, just keep the numbers, as like 0 0 1, which is just the third vector, this vector, but normalized. It's very easy to normalize it, I mean, because just have to multiply it with a suitable coefficient, namely, I mean, if you want what happens? Sorry. Okay, but yeah, the norm of this, so it's the square root of 4, it's true. So you see that, yeah, it's very easy. And then the trick is you consider u true what? So the idea is that you take v true minus the projection on the if you want the span of this one. Sorry, let's just mute this. Okay, sorry. You do this, okay, and you should know that this actually this is by definition or orthogonal. This lies in this is orthogonal to this. Should know. And what is this orthogonal projection? It's this thing. It's a vector whose coefficient is given by this. So we just have to do some computations here. So let me just, let me just copy this in the following page. Fine. I have to make a new page again. Very good. Okay. So let's do this computation now. V2 is what? 1, 2, 1 minus. So this is 1, 2, 1 times 0, 0, 1. 0, 0, 1. But yeah, this is just 1. So this is indeed just 1, 2, 0. Okay, let's see. Just as a check, let's verify that indeed 1, 2, 0 is orthogonal to this W3, and it indeed is. Very easy. And then we are almost done, because you can take W2 to be this one divided by its norm, and then its norm now is what? You just take the 1 plus 2 squared, which is square root of 5. Okay, so this is actually 1 over the square root of 5, 1, 2, 0. So in the end, orthonormal basis is given by this W2, W3, with W2 equal to this, and W3 equal to this. Fine. Quite fine, I'd say. Okay, we're done for the first one. And this is it for the first one, which was like the long exercise. Let's get to the second one. I mean, this is actually a well, this is actually an exercise where, I mean, it's not difficult, but I made it so it's like kind of tricky, because yeah, I'm considering vectors in R1. I mean, normally we think of vectors like something in plane, in space, but well, also numbers can be vectors. R1, so just the real numbers is a genuine vector space if you want. It's an example of n. If you take n equal to 1, it's perfectly okay. So linear independence, basis, and so on make perfectly sense even in this context, and everything also makes sense. So you just have to apply the definitions. Just have to remember the definitions here, and just not panic. Just think a little bit. So, is this first one independent? I mean, this is the zero vector. No, it is the zero vector. Okay, and what about the second? Well, we can check this. So you can take lambda times 5 equal to 0, but then from this you find lambda is equal to 0. So yes, it is independent. And yeah, this here, a basis for span of the zero vector. I mean, what is the span of the zero vector? You know, it's again the zero vector. So here it's kind of one has to remember this somehow, or to think about this. So what should be a basis of this? Well, let's think. A basis is a set of vectors, and the number, the cardinality of this set of vectors gives the dimension. So what is the dimension of this space? What should be the dimension of this space? Well, should accept that the dimension of the trivial space should be 0. So any basis has 0 elements. It has to be a set with 0 elements. And what is a set with 0 elements? Well, a set with 0 elements is the empty set. So the empty set is a basis of this span of V1. So, well, it's one has to remember this, but well, it works. So you see, it was pretty easy, but if one gets distracted or like just confused by the fact that we're considering just numbers here, then perhaps can make mistakes. But yeah, you have to be careful that it's not the case. So the last one, so this one is about the least square method. So let's just review it briefly before going on. So okay. Okay, so first perhaps it would be good to write down this requirement, this data set using matrices. Okay, so okay, find the line that is the closest to the following data set. So line, let's look of a line of this form. Let's say a plus bx. So you see that this has 2 coefficients, and this is what we want to know. So, and if x is equal to 1, then this a plus b has to be equal to 2. X is equal to 2, then a plus 2b has to be equal to 4. X equal to 3. A plus 3b has to be equal to 5. X equal to 4. A plus 4b has to be equal to, what is it, 4? And x is equal to 5, then a plus 5b has to be equal to 5. Okay, so you see here that we actually have a linear system we would like to solve. So it's like you have a matrix, if easy to find a matrix, 1, 1, 1, 2, sorry, 1, 3, 1, 4, 1, 5, here. This is your matrix A, and then you have like these are the unknowns you want to find, and then you have this 2, 4, 5, 4, 5, which is the, if you want, this the C vector. So we want to solve this equal to, very good. Now the whole point is that the way it's built, this is built, it's very unlikely that you can find a solution of this system, because you have many equations, many conditions, so it's very unlikely that if you find a solution, for example, from these first two ones, then it's good for these ones. But what you do is like find an approximate solution, let's say. So the idea is that instead of solving this, let me write ax equal to c. We solve something different. We solve something different, namely ax star equal to the projection on the image of A, the orthogonal projection. And now, I mean, this has a solution for sure. Why? Well, because this lives in, by definition, this lives in the image. So you can find you will be able to find some solution to this. And there is something more, namely let's wait a second. Yes, just a second, sorry. Okay. Okay, fine. Yeah, sorry. Okay, so, and there's something else. Recall that if you take C minus the projection on the image of this lives in the orthogonal. And there is a result one can invoke, that the orthogonal of the image is actually coincides with the kernel of the transpose. Just check. Yes, exactly. So it means that if you apply the transpose, if you apply the transpose to this, then it's going to be 0. Or if you want, ATR of C is going to be equal to ATR of the projection. Okay, very good. And then what happens? So if we apply the transpose, if you apply the transpose here, then what you get is that transpose okay, the transpose of this okay, is equal to the transpose of the projection of the image Yes, which is indeed transpose of this. And in nice situations, you have actually, there is a result which says that the kernel of A is equal to the kernel of this product. And I mean, normally these matrices here, they are in such a way that, for example, in this case, it's really clear that the kernel of A is 0. So here, in this case, we have 0. So it means that this is going to be a square matrix. This matrix is invertible. This is invertible. And so you can find x, this x star here, by just inverting. Sorry, this is badly written. Okay. So you can find x star by just inverting this and applying it to this A transpose of C. Okay, and this is essentially the least square methods here in this case. So this was just a recapitulation, and let's try and apply this. So, well, we have to compute the transpose and the product. So yeah, let's see, transpose, let me see, it's 1 1 1 2 1 3 1 4 1 5. Okay, so if you make this product here, well, I'm doing this just this time, but yeah. It's actually just a 2 times 2 matrix if you look. So, well, what is it here? I think it's going to be 5 here, and then it's going to be 1 plus 3, 1, 3, 6, 15 here, and again this is going to be 15. It has to be symmetric, of course. And I mean, here it's like 1 plus 4. Oh, well, 1 plus 4 plus 9 plus 16 plus 25. What is this? Well, it's 25 plus, this is 20, I think. Hope so. 5, 14, this is 20, so it's 55. Yes, so this is it. Very good, this is it. Okay, and then we solve the system, like this xy, this is the x, and it has to be equal to A transpose the C vector, which here is 2, 4, 5, 4, 5, I think, I hope. Very, very good. So, well, it's again computing stuff. What is this? So, this is, well, the first part is going to be 2 plus 4 plus 5, so 6, 11, 15, 20, I hope. I hope it's 20. Hope so. I certainly hope so. And this one is, yeah, what is it? 2 plus 8 plus 15 plus 16 plus 25. So we have 10 plus 15, 25 plus 25 plus 16, 66. Should be 66. Hope I'm not mistaken here. I hope so. I hope so. Definitely hope so. Okay. So we want. Hopefully this is the. This is the system we want to solve. And then, I mean, you just solve it. It's not much to do. If you want, shouldn't be too difficult. So take the what is it? 15 minus 15 minus 15, 3 times the first, and it's hopefully, so yeah, this is it. Well, we should divide by 5 or by 3. Well, let's see, let's just divide by 5 here. It means 1, 3, 4, and by 3 here, which means 5. No, you can't, sorry, whatever. Well, whatever. So, whatever, again. 5, 15, 20. And here, yes, 3 times this, so 0, 10, I hope. And this should be 6. Hopefully it's correct. Okay, so now we can divide the first. It's 1, 3, 4, and this is this is 0, 1, 6 over 10. So if you want, y is 6 over 10. So it's x plus, what is it here? 3/5. 9/5 equal to 4. So it's going to be x equal to 4 minus yes, so okay, so if you want the solution, final solution is what is 9/5, no, 11/5 and 3/5, and it's okay. Good, we made it, and yeah, this is it. Okay, and now as usual, let's write the solutions, which is also very important. We should have understood how to do stuff, and now let's write a nice solution, which is as always should be readable, clear, and we'll see if we perhaps will want to like we want to like not which details we will want to write down and which perhaps not really, but yeah, let's see. So let's write nicely. So exercise 1. So first, what was the answer? It's one vector, so it can't generate, and it's independent just if t is different from 0, and you can justify it this way. The one is not generating since it contains 1, which is strictly less than 3 vectors. So if t is equal to 0, then you can write this. Then v1 is the 0 vector, so it is not independent. But if t is different from 0, then v1 is independent. And yeah, an explanation, of course, indeed, if you take lambda v1 lambda times ttt is equal to, implies lambda t equal to 0, then and let's write this. Hence, again, we underline that t is different from 0, lambda equal to 0. And this is enough, actually. Okay? This is a good explanation, I think. True. Let's see. What was that? Okay. Okay. The vector, the set. Let's first write this. Being set 3 vectors in R3 is independent. Independent. Sorry, independent if and only if it is generating we consider the matrix A. You can write this if you want. Whose columns are the given vectors. Namely, A is equal to what? Let me check. Okay. Okay, so yeah, let me just copy this. TTT 121,002. I mean, just forgetting stuff. Okay, now here. Okay, well, that's quite good. Let me just okay. Okay. We modify. Well. Okay, then if you want. I'm just being a little bit redundant here. Is independent or are independent. Is independent as a set, or the vectors are independent if and only if the kernel of A is just a 0 vector. So we solve the linear system A x y z is equal to 0, 0, 0. We use Gauss elimination on A. I mean, this is very verbose. You could also say, well, the kernel is 0 if and only if the rank of this matrix is 3, and to know the rank, you just like reduce A to row echelon form by the usual row operations. It's perfectly fine. I mean, just write what you feel better. Just what makes you content and happy with your writing. And the point is always, I'm going to stress it every time. Point is always, you have to think of writing stuff which someone is going to read. So yeah, you have to be careful and like try and write nicely, and so that the reader is going to have a pleasant experience and a clear experience. And it's up to you how actually you do this, but yeah, there are of course things it's better to remember, and tricks and so on I'm giving to you. But yeah, the point, what I want to say is that it's the concept, the basic concept has to be clear. You have to think you're writing for someone, not for just yourself or just to like make sure it's just some drafty note. No, it's something you write to be read by someone, and that someone is going to wants to have a pleasant experience, and that's your goal. This is always your goal. So yeah, let's just go on. So here, and yeah, here we can be a little more schematic if you want. I mean, here now, when you master some technique, then you like you find yourself some ways of writing stuff which is like compact yet still clear. So for example, here you say that you can do 2 minus 1, 3 minus 1. Okay, so here I mean that I'm replacing the second with the second minus the first, and the third with the third minus the first. And so, which is then 0, 1, 0, 0, 0, 2. I hope it's correct. I hope so. T1, 0, 0, 1, 0, 0, 0, 2. Okay. Okay. Well, it seems so. And is it? You don't have to do anything right now here, like, right? Forgot. No, it's fine. And so, the associated, let's see, the associated linear system is, well, tx plus y is equal to 0, y is equal to 0, true, z is equal to 0, from which we deduce y equal to z equal to 0, and tx is equal to 0. Another page, yes. So if t is different from 0, then also x is equal to 0, and indeed the kernel of A and V1, V2, V3 is a basis. Which is the answer. If t is equal to 0, then any vector of the form x 0, 0 lies in kern for any number x. Hence, I'm not independent and they're not generating. Okay. Okay. It was a little bit longer, but yet, yeah, that's okay. Fine. 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 We go on. We go on. It's correct. Yes. Okay. The third. So we have all the three vectors. So v1, v2, v3, v4, linearly independent and generating. So, which is the third point? Yes. Okay. So the first thing you can write is that v1 are not independent because it is set of 4 greater than 3 vectors in R3. Next, we show that actually this v2, v3, v4 is a basis and this will imply that is generating. Okay, so as we said, if you have a basis, then it's generating. Then if you extend it, it's still generating. Indeed, consider the matrix and A. It's not the same A, but yeah, it's. I mean, it's okay even if you reuse some symbols in different parts. I mean, the point is it clear? Is it confusing? I mean, from the context here, it's quite acceptable and clear that this A is not this A, so it's fine. If you don't really want to be, if you don't really feel like it, just give another name. It's okay. So okay, which is this? Let me copy perhaps. Where are you? 1 2 wait 1 2 1 0 0 2 1 0 0 1 2 1 1 2 1 0 0 2 1 0 0. Okay. Okay. We modify B with row operations. I mean this if you write row operations, then it's clear that it's also clear that you're using the Gauss algorithm. If you want to specify it, it's fine. Okay, so well, you can take this And then from here, what you do is, like on the second, you replace it with the second minus the first, and the third, you replace it with the third minus the first again. So, not minus the first, minus 2 times the first, better. Okay, okay, very good. Very good. So, 1, 0, 1. There's an error here. No, there's not an error here. So 0, 0, minus 2, I hope. Is it correct? Or was I wrong before? No, 0, 0, minus 2. Well, it's fine. And yes, 0, 2, 0. Fine. And then, yeah, you can, for example, exchange okay, if you want 1, 0, 1, 0, 2, 0, 0, 0, minus 2. And here, well, you can, yeah, you can if you want, and also the third. Okay, so you put it here, 0, 1, 0, 0, 0, 1. Yeah. And this is the, so it is clear, that the rank of A is 3. So the rank, you remember, it's the number of leading ones, but you don't have to recall it. Hence, if you want, kernel, oh, it's not A, it's B, sorry. B is equal to 0, and V2, V3, V4 is a basis as claimed, and it's okay. Then this is the proof that this is a basis, but we've already said that if this is a basis, then the bigger set is going to be generating, so it's perfectly clear. Okay, we go on, new, and here now comes, I think, the orthogonality part. Yes, so a basis of the subspace span V2 orthogonal, 1, 2, 1 orthogonal, okay, 3, let's see, 3. Okay, span of this orthogonal is well, let's not be so abrupt. We have, let's write. I mean, it's nicer if one writes and so when you read, it's not just like formulas and nothing else. Okay, like this. What was that? 1, 2, 1. Okay, fine. Equal to 0. So you can go on here. X plus 2y plus z is equal to 0. Okay. Okay. So So what can I say? An arbitrary element write this is of the form, well, xy, and then z is equal to minus x minus 2 times y, so xy minus x minus 2 times y, so which is equal then to x 1 0 1 plus y 0 1 minus 2. So is it correct what we are saying here or not? 1 0 1 0 minus 1 1 0 1 minus 2 minus 1 here. We conclude that the basis of this span is given by given by okay, so, and this is it. Okay, 4. This was the last one of this exercise. So it was the Gram-Schmidt algorithm, right? Let me just do, can 1 0 minus 1 0 1 minus 2, is it correct? 1 0 minus 1 0 1 minus 2. Oh, yes. So here we apply the Gram-Schmidt algorithm, starting from the V3 we normalize it, we set W3 is equal to V3 divided by its norm, which is 0 0 1. Then we define U2, sorry, which is equal to what? V2 minus the projection on the span of V2. And this is equal to, well, V2 is equal to 1 2 1 1 2 1 minus so you have this 0 0 1, and then the coefficient is what is the inner product between okay, so 1 minus minus 0 0 1, so which is 1 2 0. We then set W2 equal to U2 divided by its norm, which is, yeah, it's kind of easy. An orthonormal basis of this span v through v3 is given by what? The w through w3. Okay, and this is it. So we made it for the first exercises. I think it's everything. It was not so fast, but yeah, this is it. This is how you can write a solution for this first exercise. Okay, so we have two more to go, but they're quicker. So well, this one is very short. So exercise 2. So okay, very quick. Is not. Oh, handwriting is not independent since v1 is equal to 0. Is the 0 vector. So the other v true is independent. Oh, independent. Indeed. For any lambda, we have that lambda times 5 equal to 0 implies lambda equal to 0. That's okay. And the last one, we can just say span 1 is the trivial subspace of R1, I want to, okay, hence a basis thereof is given by the empty set. Okay, this is it. This was very quick. Okay. Yeah. Just the point of this exercise was just to make you think about that concept. Think that concepts in linear algebra can be applied also to like trivial setting, which is just one-dimensional vector space, which is just made by the real numbers. So the line, just the line. Okay. The last one, finally. Okay. Okay, very good. So let me exercise 3. Okay. I'm going to write a quicker solution here. Exercise 3. Okay, so the point here is organizing the data. So let's just be clear about this. We organize the data with the following matrix A. This is what is it? Ooh, 1 1 1 2. Okay, 1 1. And C equal to 2 4 5 4 5. Okay. We are looking to approximate all the A okay. Well, it would be nice here to make the reader know that the way this matrix is built is related to the fact that, yeah, this is just for x equal to 0, for x equal to 1, equal to 1, to 2, to 3, to 4, to 5. Then it's what the y is. I mean, if you look at the coefficients, it should be nice. It would be nice to make it clear, but it's not very easy. It's something you sometimes have to accept, that you can't explain everything in your solutions, and sometimes things are going to be not clear for everyone, even if your efforts are the best possible. There is always something you take for you let's say, there is always something you take for granted when you write solutions. For example, you accept that you have some theory that you know, and that you assume that the reader knows, and so on. So as you see, writing solutions is not really an easy task. It's like you also have to think, well, who is your reader? I mean, your reader is someone who wants to learn this stuff, so you're going to write a book on this, or is someone who you can assume it's his, or let's say they are kind of knowledgeable. And well, it depends. Here, let's say we're writing solutions as detailed as possible, but we're assuming that throughout here, if you look at even at these last solutions we've made, we somehow assume that the reader knows some concepts. So they know what linear independence is, they know what the basis is, and so on. And even here, we can also assume that they know how to, they know that organizing the data, I mean, if they know that they should, when they see this matrix, they understand that this is the right way of organizing the data. If you want, you can say something like this: A and B are thought as coefficient we want to find. Okay, so this helps perhaps, because then he sees, well, this is 1 and y is equal to, and if x is equal to 1, then you have this like a plus b, and then you have, it's not really this actually, a plus bx. Okay, now it's correct. If x is true, then you have this and this and this. Yeah, it's better. It's a good compromise. I would say it's a good compromise. But as I said, here you're writing solutions. Well, when you are at an exam, you can of course think you're writing a solution for your teacher, who you can assume is knowledgeable, is kind of an expert. Still, you don't want to omit the details because you want to convince him that you know stuff, and you also know how to write stuff. So the point here is, okay, think about who your reader is and tailor your solution to this. In general, be as detailed as possible. You can assume that the reader knows the theory you're using, and you can also assume that he's like smart enough, if you want, to understand tricks like this, the way we organized the data in these matrices. It's a kind of a trick, but yeah, you can if you want assume that the reader is also knowledgeable on this. But if you don't feel good with this, it's nice to make some more explanations here. I mean, with this, that I would consider a good explanation, personally. Without this, perhaps we miss something, but still it would be okay, I guess. In any case, as I said, the point is always think about your reader. You can assume some basic knowledge, and the basic knowledge you can assume is like depends on the context. But here, if you're doing a linear algebra exam, you can of course assume that your reader is going to understand all the theory and the tricks. It's okay. Be detailed, be clear. Yeah, I'm repeating myself, but it's very important. So let's go on. And here, yeah, for example, you don't have to rewrite and re-explain all the least square methods, but you can just like assume that it's part of the theory. So you just apply it. Okay. Using the least method. Look. So it is A transpose A. Let's say X star equal to A transpose C. And also another thing here, you look here that there are some computations. I mean, here it's matrix multiplication. At some point, you don't have to redo it. Here, the point is not really the computations. The point is really the method, the procedure. So you can streamline this. You can like take a risk and just write something like a computation, direct computation, gives, well, A transpose A is equal to 5, 5, 15, 15, 55, yes. 5, 55, 15, 15, and equal to what is it? 2066. Okay, and here, if you want, I mean, you assume that you have a draft of your like solution here, and I mean here you're let's for this time let's take another risk here, which is a little more than just direct computation here. You can, if you feel like to, in an exercise like this, where actually the solving the linear system by itself is not really that important. I mean, the solution is what it is. It's like 2 times 2 matrix. It's like 2 variables. I mean, it's nothing strange. And you have your draft here. Perhaps it's not so badly written. So yeah, it's kind of clear here. So you can say, well, I write this. Solving you can say also the C drafts for details. We find out that x is equal to okay, 11/5, 3/5. Okay, I mean, I'm saying it's really taking a risk here, because I mean, say you're doing an exam, then well, solving a linear system, well, one could say, well, it's a crucial part of I mean, knowing how to solve a linear system is like part of what you should know, and so you should actually be more careful here. And we were actually very careful in many other occasions where the exercise was like solve this linear system. But well, here, why am I taking this risk here? Well, there is a reason, and the reason is actually the linear system here by itself is not the crucial part. It's not really what you want to show that you know. It's not really the thing that you want to make the reader aware of. I mean, if you look at this exercise sheet, we probably already solved a lot of systems, a lot of linear systems, and yeah, perhaps at some point this is the last exercise. So yeah, who reads perhaps is now convinced that you know how to solve a linear system, and perhaps now he's willing also to accept that the solution are like kind of found in a straightforward way. And I mean, there are no parameters here. There are nothing that can go wrong here, and so it's like, and I mean, the exercise is really about these least square methods. So the point is this you have to remember, and this is the important thing, right? Yes, exactly. This is the important thing. So, and once you have this, then yeah, the rest is not really crucial to the solution. It's like just, yeah, at some point it's like just 2 times 2 linear system without any parameter, without any subtlety. and also you refer to the drafts. I mean, this makes everything safe. I mean, you can attach your draft, and then who reads can go back and look at it, and this makes this solution perfectly safe. So we are taking some risks here, but not really. I mean, we are still saying this. If we didn't, that would have been a risk we took. But still, it was like very risky, but kind of reasonable. Because, as I said, the exercise here, the crucial part of the exercise is not really this linear system. It's just recalling this and knowing how to and knowing that this is the correct thing to recall. Okay? So this is it. In any case, I would advise you in these cases when you feel like that, solving a particular linear system is not really the crucial part, but of course it's kind of risky not to write it in the solution. Then okay, it's less risky. It's okay if you attach your drafts, which by the way are not so badly written. It's kind of clear here what's going on after one has read through some Gauss eliminations. Then they are mostly the same every time. So okay, you can attach this. It's okay. This makes it definitely not really risky. But yes, I hope the point is clear. It's a choice you make. Everything when you write solution, you are making choices. You are choosing what the reader is going to read. And as I said, the point is you want them to have a nice experience. I'd say, well, writing something like this and referring to some drafts and some computations here, it's perfectly okay. It's perfectly okay. Well, perhaps even better, you can put some marker here if you want, and then here so that they have a reference. It's even better, but yeah, that would be acceptable. Also writing the detailed solution here, that would have been acceptable. Not having this, well, risky, but still, if you convinced the reader that you indeed can solve linear systems, and if he after the other two exercises if they have already seen some linear systems, then perhaps, why not? But yeah, I'd say don't take any risk. But if you don't feel like to rewrite computations you find just straightforward, in this case there is nothing that can go wrong. There are no parameters, no tricky things, so you can refer to your drafts. In this case, it will be okay and acceptable and not very risky. So yeah, okay. I hope this is kind of clear, and we'll see each other again next week with something about determinants. So yeah, thank you.